A server somewhere, copying data it cannot read. Not because it can read it, because it's waiting. The countdown already started, you just didn't know. The quantum leap. Right now someone is copying data they cannot read yet. The quantum leap, one lap, one measurement, one countdown. This is not a future threat, it's a present strategy. The NSA warned about this in 2015. Quietly, but they stopped recommending elliptic curve cryptography without explaining why. Security researchers spent years guessing. The answer was straightforward. The NSA had run the numbers on quantum impact. They didn't want panic, but they knew what was coming. In 1994, a mathematician named Peter Shor published an algorithm. On a quantum computer, it factors large numbers fast. RSA encryption depends entirely on that factoring difficulty. Shor's algorithm dissolves that assumption in seconds. 90% of encrypted internet traffic runs on RSA. Your banking, your medical records, diplomatic cables, military communications, all secured by the one problem Shor's algorithm solves. In 1994, the machine to run it didn't exist. It required qubits, quantum bits existing in superposition. Qubits are extraordinarily fragile. Any interference destroys computation. The race builds stable qubits before encryption breaks. For 2 decades, quantum computers were too small and noisy. Then 2019, Google's Sycamore processor claimed quantum supremacy, solved a benchmark in 200 seconds. Classical computers, 10 years. IBM disputed. Classical computers could do it in days. What strikes us about this debate, it didn't matter. The benchmark wasn't the thing, the trajectory was. Now, let's look at what the science actually shows. November 2023, IBM Condor 1121 qubits. But qubits aren't equal. Physical qubits make errors constantly. You need logical qubits, error-corrected clusters of physical qubits. Breaking RSA 2048 requires 4,000 logical qubits. At current error rates, roughly 4 million physical qubits. That gap is the timeline. That gap is closing. IBM's public roadmap targets fault-tolerant quantum by the 2030s. Not breaking encryption. Fault-tolerant quantum, the precondition. What happens between fault-tolerant and cryptographically relevant? Months, maybe less. That's what the physics tells us. Mikhail Mosca, 1 in 7 chance of RSA break by 2026. When we read that figure, we check the methodology twice. His methodology was sound. His estimate was conservative. The US government's official estimate, early 2030s, a decade. That's the public estimate. The classified estimate may differ. We acknowledge this is inference, not reporting. It holds. Because of December 2024. Because of a chip called Willow. Google's Nature paper described exponential error rate reduction. As qubit count increases, errors decrease. Exponentially. This reverses a decade of assumptions about quantum scaling. If you've been tracking this story, a note. Subscribe. The quantum timeline is changing monthly. December 2024, Google published a chip called Willow. Most headlines called it a computing milestone. They missed it. What headlines missed? The error rate curve in supplementary data. As qubits increase, errors decrease exponentially. This changes everything. Plot that curve against IBM's roadmap. You get a window. Earlier than anyone is publicly acknowledging, we report data. To be precise, this is a projection, not a prediction. Quantum timelines have been wrong before. Fusion taught us. But the Willow data is different in kind, not degree. Previous milestones were noise floor improvements, linear progress. Willow showed a feedback loop. Better qubits improve error correction. Better error correction enables larger coherent quantum states. Larger coherent states enable more complex quantum computations. This is not linear, this is the feared feedback loop. Two separate developments, so far parallel. They aren't parallel. The convergence point is where cryptographic relevance begins. NIST saw this coming in 2016. They launched a competition. 69 submissions worldwide. One goal: survive Shor's algorithm. The defense is official, but the offenses moved faster. August 2024. NIST finalized 3 post-quantum cryptography standards: Crystals Kyber, Dilithium, SPH INCS+. The new cryptographic standards. These call Stellar. ASCII resistant. Also 5 to 10 times slower. Migration has real costs. Processing overhead, infrastructure replacement. Most Fortune 500 companies haven't started, roughly 15%. The US federal deadline 2030. 6 years. Clock running. The banking sector processes $5 trillion daily. All RSA. What happens if RSA breaks before migration is complete? It's 2033. Your bank app shows an unfamiliar balance. Not a traditional hack. The encryption was mathematically solved. Every transaction log from the previous decade now readable. That scenario assumes breach before migration. Here's the question. Is migration time shorter than the quantum threat window? We don't know. That uncertainty is the most important fact. Consider Bitcoin, $1.7 trillion secured by elliptic curve cryptography. Shor's variant also breaks elliptic curve cryptography. Every Bitcoin wallet with an exposed public key is vulnerable. Satoshi's original wallet, potentially vulnerable, untouched since 2010. $200 billion in early-era Bitcoin, potentially exposed. The Bitcoin community knows. The migration plan hasn't started. We see this pattern across every domain. Plan without urgency. What strikes us, we've seen this film before. UTK succeeded because mandates and hard deadlines force migration. The quantum migration has a deadline. 2030. Enforcement unclear. There's a deeper issue. One we haven't named yet. Harvest, now, decrypt later. We mentioned it at the start. Adversaries don't need to break encryption today. Collect encrypted data today. Decrypt it in 10 years. CISA confirmed this is happening. State actors, active operations. Bitcoin holds $1.7 trillion secured by one algorithm. Elliptic curve cryptography, a cousin of RSA. Shor's algorithm breaks both. Peer-reviewed. Published 1994. A quantum computer running Shor could drain exposed Bitcoin wallets. The Bitcoin community knows. The migration still hasn't started. That gap is the story. Full breakdown in the comments. Now, diplomatic cables. Security archives. Military communications. Everything encrypted in 2000 and 2004 that adversaries collected archived. DT estimates the economic impact at $30 trillion. What does this mean for us? For the next decade? The mathematics of public key cryptography has an expiration date. Not because quantum computers will definitely break it by 2030. The window may be shorter than migration requires. NIST post-quantum cryptography standards are real. They work. The problem isn't the cryptographic solution, it's institutional inertia. Dustin Moody at NIST led the 8-year competition. 69 submissions. Standards done. Now comes the hard part. Moody, 2024. The hard part is migration. Every organization faces it. TLS, SSH, VPN, certificates all need quantum-safe replacement. John Preskill of Caltech. coined quantum supremacy in 1997. He leads Stellar Quantum Institute. His 2024 assessment is cautious. He doesn't say RSA breaks by 2030. He says attend. That gap, data versus expert consensus, is expected. We're reporting in that gap. We find it intellectually compelling. Here is a framework for assessing your organization's quantum exposure. Short shelf life data, commercial transactions, lower quantum risk. 30-year sensitive data, medical, intelligence, IP. High risk. Which category does your critical data fall into? If high sensitivity, long duration, migration planning starts now. The Quantum Leap built this framework from 3 primary sources: NIST's Migration Guide, CISA's Threat Assessment, Moscow's Probability Model. Each carries different evidence weight. We've been transparent about that. What we find compelling, the convergence of all 3 independently. Independent sources, different methods, same conclusion reached. Post-quantum migration is not optional. Most organizations are already late. In one version of 2035, this ends mundanely. Migration completed, quantum arrived, nothing broke, normal infrastructure. In the other version of 2035, the story gets complicated. Most infrastructure still runs RSA. The quantum computer arrived first. The difference: decisions made in the next 3 years, not a congressional vote. Each organization's individual decision. We don't know which 2035 we're building. That's honest. Jay Gambetta at IBM is running the roadmap right now. Dustin Moody is building implementation guidance for his standards. Your IT team is deciding whether migration budget gets approved. These decisions are connected. The aggregate shapes which 2035. Peter Shor is 66 now. He published this at 36. He didn't expect practical implementation to arrive this fast. The science doesn't ask permission from institutions catching up. The first post-quantum generation has already been born. Watch the Fall investigation. Link below.